Hello, Divyangi and Hiba.
Good evening, sir.
Good evening. So we were discussing the angular momentum. So first we will revise angular momentum. So angular momentum is r cross p. Okay, and r is the, you can say, position vector, and p is the linear momentum. In vector form, this is the formula. And if you want to calculate the angular momentum magnitude, then in this way you can calculate mass into r, okay, r, and perpendicular component of velocity, or in another way you can calculate the angular momentum mass into velocity into perpendicular, means the perpendicular component of r. So I told you when we were solving the numericals, number of numericals we solved. So we have done questions. Now we will discuss when a particle is moving in a circular path. When a particle is moving in a circular path, then what will be the angular momentum? Okay. Angular momentum angular momentum of object moving in a circle, moving in a circle. Okay, so we'll take circular path. This is a circular path, and suppose this is mass m, and this mass m is moving on this circular path. So this mass m will move in a circular path like this. This will be the direction of the linear velocity, and this is mass m of the particle. After some time, then this particle is moving in clockwise direction. Okay, sorry, anti-clockwise direction. After some time, the particle is here, and the direction of the velocity of the particle will be tangential like this. So this will be the direction of the velocity, and mass m is there obviously. And after some time, the particle is suppose here, and the velocity of the particle is in this direction, that is v. Particle is here, particle having mass, and after some time the particle is suppose at this position, and the direction of the velocity will be tangential, v. Okay, and this is mass m. Okay, now this is the center of the circle about which the particle is moving. Okay. Now what you should do, suppose this is one position, this is second position, third position, fourth position. So this is first position, second position of the particle, third position of the particle, and fourth position of the particle. Different position of the particles during the motion. This is first position. Okay. Now what we should do for the first position, first we will calculate what will be the angular momentum. So for that, what we should do, this is the direction of the velocity, and this is the position of the mass. So we will join this with center like this. So this will be r. This will be r perpendicular, or you can say r. And this is the velocity. Now you can see here r and velocity both are perpendicular. So we can apply mv into r perpendicular, the formula of the angular momentum. We can apply mv r perpendicular. What is the meaning of mv r perpendicular? M is the mass. Okay. R perpendicular means the component of the R which is perpendicular to velocity, but here R is perpendicular to velocity. So angular momentum at position 1 is equal to mass into velocity into R perpendicular. R perpendicular is R here. This is perpendicular, okay, already perpendicular to velocity. So M V into R. Okay, now we will see what will be the direction. We will see what will be the direction. And what I told you about the direction, for calculating the direction, just extend the R. Extend the R. This is the R. This is the R. Now R cross B. R cross B. R cross B means this direction. Which is this direction? Anti-clockwise direction, na? This is anti-clockwise direction. And I told you anti-clockwise direction is the outward direction. So angular momentum will be outward due to this. Okay. Means when the particle is at position 1, the angular momentum is outward. Okay. So angular momentum will be mvr and it will be outward like this. For L2, this distance will also be r, same distance. This will also be radius, and this radius will also be perpendicular to the velocity. And you will apply for calculating the angular momentum here, mv into r perpendicular. So mv r perpendicular is this. mv r perpendicular. This is also mv r perpendicular. mv r perpendicular r. Okay. Now for the direction, extend r. So when you will extend r, this in this direction will be r like this. And you will go from r to v. So this direction will be anti-clockwise direction, and anti-clockwise direction I told you is considered as the outward direction. So here also the direction of the angular momentum will be outward. Mean at every point on the circle, the magnitude and the direction of the angular momentum is not changing. Okay. On this point also, you can check at any point, and at any point, the magnitude and the direction of the angular momentum will remain same. In case of circular motion, there is a constant magnitude and direction of angular momentum. So this dot is representing outward direction. Outward means towards the reader or away from the screen. Towards the reader, you can say. Towards the reader. And this, there is one more cross. Away from reader. Away from reader. Away from reader. So you will calculate all the angular momentum. So in case of the circular motion, uniform circular motion, remember this magnitude of the velocity is not changing. The magnitude of the velocity is not changing. So you can write in case of uniform circular motion, in case of uniform circular motion, the angular momentum remains same in magnitude and direction. The angular momentum remains same same in magnitude and direction. In magnitude and direction. Okay, so if a particle is moving, this is the same particle moving on a circular path in anti-clockwise direction. So the magnitude of the angular momentum and the direction of the angular momentum will remain same. And I told you angular momentum is the axial vector. So the direction of the angular momentum is not anti-clockwise or not clockwise. Anti-clockwise and clockwise just for the identification. Real direction of the angular momentum will be away from the axis or towards the axis, means along the axis it should be. Means if this is anti-clockwise, I told you that anti-clockwise is considered as outward. So here the angular momentum is outward, means each and every point the direction of the angular momentum will be outward. Okay, so write down please. Okay, now we will discuss the angular momentum of the rigid body. Earlier, what we discussed, angular momentum of a discrete mass. There is only a point mass and that point mass is moving, and we were calculating the angular momentum. Now we will calculate the angular momentum of the rigid body. Suppose this is a rigid body, and this rigid body is rotating about some axis like this. Okay, there is an axis passing from here perpendicular to the plane, or this can be rotating like this also. Any way it is rotating. Okay, so this is rotating like this. Okay, about this axis perpendicular to it, and we want to find the angular momentum of this body. So I am taking any random rigid body, and what we will consider there, we will consider that rigid body is made up of large number of small masses. And what is the criteria to find the angular momentum of the rigid body? First, we will calculate the angular momentum of discrete masses of means I told you that in the starting, remember, in the starting what I am telling, the body is made up of large number of masses, different discrete masses. Okay, first we will calculate, and one more thing, the body is rotating about a fixed axis. We will calculate the angular momentum of all the masses about that axis, and we will add vectorically the angular momentum of all the masses, and we will get the total angular momentum of the rigid body. So for example, this is a rigid body, and earlier also I used this rigid body to derive the kinetic energy expression. So I am not wasting time in drawing. So this rigid body is rotating with an angular velocity of omega with about this axis like this. And these are the masses. I have taken 3 masses, but this body is made up of large number of masses, and this is a rigid body. So the meaning of the rigid body is that during the motion there will be no change in the separation between any two masses, and this cross is representing the axis of rotation. Cross means into the body. Cross means into the body, inward. And this omega is the angular velocity. And I told you that these masses m1, m2, m3, any mass on the body will have same angular velocity. If this rigid body is rotating with an angular velocity of omega, then each and every mass of this body will also rotate with an angular velocity of omega, but the linear velocity can be different. Linear velocity can be different. This v1, v2, v3 can be different, but angular, you can choose any mass. I'm choosing this mass m1. For this mass m1, the omega and angular velocity will be omega, but the linear velocity will be v1. For this mass m3, the angular velocity will again omega, but the linear velocity will change, that is v3. Okay, so in case of the rotational motion, the angular velocity of all the masses, actually now what happens in case of the rotational motion, all the masses perform the circular motion. Okay, and if the masses are performing the circular motion, they are completing equal angle in equal interval of time. That is why the angular velocity of all the masses remains same. Okay, so we have chosen 3 masses, and remember, this is the assumption that this is a rigid body and this body is made up of large number of masses, and I am taking only 3 masses. Okay, so we will calculate the angular momentum for the first mass, second mass, and the third mass. So total angular momentum, if I want to calculate total angular momentum, so here I am writing angular momentum of purely rotating body. Angular momentum of purely rotating body. Purely rotating body. Or you can say a rigid body rotation. So one by one, we will calculate the angular momentum. First, we will calculate the angular momentum of mass 1 about this axis, because the body is rotating about this axis. Then for the mass 2, we will calculate the angular momentum about this axis, and then for the mass 3. So total angular momentum, okay, total angular momentum, we will calculate vectorically. Total angular momentum is equal to the angular momentum of, because angular momentum is a vector quantity, L1 plus angular momentum L2 due to mass 2 plus angular momentum L3 due to mass 3 plus, and there are n number of masses in this model. Okay. Now this is I have written in the vector form. Now total angular momentum is equal to, now we can write for the mass m1, m into v1 into r perpendicular, m v1 r1. What is the formula for the total angular momentum? Formula for the angular momentum. Angular momentum is given by mv into r perpendicular. So now you can see here m1 into v1, and which r is perpendicular to v1? This r1 is perpendicular to v1. r1 and v1 are perpendicular. So what is the angular momentum of this mass? m1 v1 r1. m1 v1 r1. One more thing, direction. See, for direction, what we will do? You will extend this r like this, and now you will move r to v like this. So this is anti-clockwise, means outward. Okay. So anti-clockwise means this angular momentum is outward. Due to mass m1, the angular momentum is outward. Okay. So here you will write plus angular momentum due to another mass m2. So it will be m2 v2 into r2. Simple. m2 v2 into r2. Now what you will do? You will just extend this r2 for the direction. So this will be r2, and you will move like this. So this is also anti-clockwise. So this is also outward. So it will also outward. So it will be also like this. Plus similarly m3.
So,
yeah,
it's not clockwise.
it's not clockwise, it's anti-clockwise. You can see here. Which one you are saying?
Or m1 v1 r1.
m1. No, actually no, what you have to do, this is m1 na? So see what is r here. No, you will extend this r. This is r, and you will extend this r like this. So this is the direction of the r now. This is r. So you will move from r to v. So this direction is anti-clockwise now or clockwise? It's anti-clockwise, huh? This direction.
Oh, it's clockwise. No, it's anti-clockwise.
This is anti-clockwise, huh? Okay, okay. So in this way, I am not drawing all the things here. The diagram will become very bad. That is why I am not drawing all the things. Okay, I will wait for 1 minute. Okay, so similarly for M3 also, always for the direction of the angular momentum, you have to move from R to V. You have to move from R to V. Do not use the right hand rule. Okay, here what thing you should use, move R to V. If you are moving R to V anti-clockwise, then direction will be outward. If you are moving R to V clockwise, the direction of angular momentum will be inward. So, but if you are moving from R to V and you are getting anti-clockwise, then you cannot say that the direction of the angular momentum is anti-clockwise, because anti-clockwise is not a direction. Direction of angular momentum will be axial always, because this is an axial vector. The anti-clockwise and clockwise are just for easy understanding. So for this M3, angular momentum will be M3 V3 into R3. M3 V3 into R3. V3 into this will be also inward, outward. This will be also outward. Similarly, all the direction, if you want to calculate, all the direction of the angular momentum will be outward. So we can add all the angular momentums. So total angular momentum of the body is equal to m1 v1 r1 plus m2 v2 r2 plus m3 v3 r3, because all are in the same direction. We can add. Suppose if any one of the direction is like this, cross direction, then what we will do, we will write, if one of the direction of the angular momentum, it can be, you will find in the question, if one of the direction is cross means inward, and one of the direction is dot means outward, then in this case what you will do, you will write for the total momentum, you will write m1 v1 r1 minus m2 v2 r2. But here not fortunately, I will say, here we will have this. Okay. So we can easily add. We will have m1 v1 r1 plus m2 v2 r2 r2, okay, plus m3 v3 r3, and similarly we have m1 m4 v4 r4, m5 v5 m5 v5 r5, 6 7 8 9 10. Okay. Okay. So now there is a relation between this v1 and r1. v1 is equal to r1 into omega, v2 is equal to r2 into omega. Okay, this is a relation between the linear velocity and the angular velocity of a rotating body. Similarly, for v3 is equal to r3 into omega. I told you this relation is valid. So many times in each and every derivation we are using this expression. So here, instead of this v1, we will put r1 into omega. So total angular momentum, I am representing the total angular momentum with only L, capital L. So this is L. This will be m1. Instead of v1, we will put v1. What is v1? r1 into omega. We will put r1 into omega and multiplied by r1 plus m2. Instead of v2, we will put r2 into omega multiplied by r2 plus m3 into v3 means r3 into omega multiplied by r3. Okay, so after this we will have, this is m1, this omega, here is omega, na? Here is omega, here is omega, here is omega. So omega will be you can take common from all the terms. Okay, from all the terms we can take common omega. Omega is common, and finally here will be m1 into r1 square, m2 into r2 square, m3 into r3 square. So it will be m1 into r1 square plus m2 into r2 square plus it will be m3 into r3 square plus and so on. And so angular momentum L is equal to, this is omega. Now this term is something we already know. if I will take all the masses and I write the sum of m1 r1 square, then it will become total moment of inertia of this body, m1 r1 square plus m2 r2 square plus m3 r3 square. So total moment of inertia. This is the moment of inertia. About which axis? About this axis. Axis is all important. So L is equal to omega into I. So final formula is L is equal to I omega. Now I can compare this with the linear motion. This is the formula we have in the rotational motion. This is angular momentum. In rotation motion, we have angular momentum I into omega. But in case of the linear motion, what we have? Linear momentum, mass into velocity. So now I told you in the rotational motion, instead of mass, there is a moment of inertia. Instead of linear velocity, there is an angular velocity. So there is an analogy between the two. So finally, you will get this formula L is equal to I into omega. Okay, so write down this. Scroll down. Okay. Now we'll solve one question. On the same concept. There are two masses. One mass is this, and these are 2 point masses, okay? And like this, and there is an axis. This is an axis, and about which both the masses are rotating with an angular velocity of omega. And the distance between the two masses is L. Distance between two masses is L, capital L. We have to find the angular momentum of rod. Just a minute. No. Angular momentum of this system. System of masses, we have to calculate the angular momentum. So this is the center here. Okay, and these two masses are rotating. So for calculating the angular momentum, we'll apply L is equal to I into omega. Angular momentum of the system is equal to the moment of inertia. Angular momentum about this axis of the masses is equal to the moment of inertia about this axis multiplied by angular velocity about this axis. So moment of inertia about this axis will be, this is the axis of rotation. This distance will be L by 2. And this distance will be L by 2 for this mass. So moment of inertia for this mass will be m into L by 2 square, because mr square is the moment of inertia of this mass. So it will be m into L by 2 square. Plus there is another mass also in the system. This is m multiplied by perpendicular distance square, that is L by 2 square. And this is moment of inertia I, and there is an omega. There's an omega. So it will become m L square by 2, m L square by 2 plus m L square by 2. It will become 2m into L square by 2 means L square by 4 into omega. So 2 to the 4. So the answer will be ml square omega divided by 2. ml square omega divided by 2. This will be the answer. This will be the answer of this question. Okay, please write down. Please write down. So two masses are there.